My name is Andrew Gary.
My name is David Ewart.
And this is our ballistic pendulum experiment.
We have some equations that we want to go over first. The main equation is P before equals P after. It basically says that momentum is conserved. The way that breaks down with the ballistic pendulum is that we have the mass of the bullet and the velocity of the bullet plus the mass of the pendulum and velocity of the pendulum before equals those variables after. And when you break that down, we get the velocity of the bullet. When we want to solve for that, we take the mass of the bullet and block times the velocity of the bullet and block, and we divide all of it by the mass of the bullet, and that'll get us our value for velocity bullet alone. The way we get velocity is we take 2 times the gravitational acceleration, which we're using 9.8 as our value, times the height that the pendulum swings. In summary, we can also kind of shorten the whole equation into velocity bullet equals 1 plus mass block divided by mass bullet times velocity, which is equivalent to the square root of 2 times g times h. Our variables that we're using in our equations, v stands for velocity, p stands for momentum, g stands for gravitational acceleration, and h is height in meters. The ruler that we're using is in inches, so there is a conversion that we have to do from inches to meters.
This is a picture of what our pendulum is going to do, and we need to calculate how high from the starting point to the ending point the center of mass goes above the ruler.
So this is going to be our wood block that we're going to use for the pendulum. We're going to wrap it in tape, and we're going to drill 2 screws in it because we're going to use 2 strings for our pendulum. That way the block stays straight and doesn't keep spinning. We've done some trial runs with this before. If you use just 1 string, the block wants to keep spinning, and it makes it really difficult to get a nice even shot. The reason we're wrapping it in tape is we don't want pieces of wood splintering off and changing the mass of the block. It's important to keep everything the same as you go through the experiment. So there we go. And then we want to drill a couple screws into this. Okay, so the one thing that we did want to do is to try to get an idea of how far back we would have to be so that the air only doesn't affect the pendulum at all. So the first shot's going to be at 6 inches. So we still get quite a bit of movement at 6 inches. Let's go ahead and try a foot. That's 2 feet. Determine that 2 feet is about the distance that it takes for the air not to affect the pendulum swing. What we're trying to do is just isolate the bullet to find out exactly what the velocity of the bullet is, how it affects the block, and plug all that data into our equation and eliminate the error factor. So we'll get back to you as soon as... Okay, so we have the block all set up. As you can see, I put a black dot on it. That's to give us an idea where our center of mass is. I also set up a ruler. The ruler is going to make it easier to get an idea of how far it swings and what the height is. I know from previous experiments that we're going to be somewhere around 26 inches with the mass that we have for the wood block. We can adjust that after the first shot just so it's a little bit more lined up. Now what I did is I took a level and I went from the dot here to a mark on the tape measure, That way we know exactly where the center of mass lines up with the tape measure. Fire 1 BB, point blank. Fire 2 BB, point blank. Fire 3 BB, point blank. To the third shot, or we'll have to make the adjustments depending on how it all works out. The next 3 shots that we're going to make are going to be with pellets. One of the pellets sounds like it ricocheted out. There's probably still some lead in there, so we're just going to have to kind of give it a value of 1/2 of a pellet and just kind of guesstimate. Fire 1, distance of 2 feet, BB. Fire 2, distance of 2 feet, BB. Fire 3, distance of 2 feet, BB.
This is the velocity for our BBs. Velocity equals the total mass of the pendulum, which is 59.04 grams, divided by 0.327 grams. The total of that comes to 180.55 grams, times the square root of 2, the acceleration of gravity, which is 9.8 meters per second squared, times 0.1683 meters, and that is our height. That total came to 327.92 meters per second, times 3.28 feet to convert it into feet per second, and our total came to 1,075.58 feet per second. Our velocity for BB shot 2 was 1,007.73 feet per second, and our velocity for BB shot 3 was 1,131.53 feet per second. On shot 2, you will see the addition of mass from the additional BB, and it comes to 59.37. And on shot 3, there was a ricochet, so the mass did not change. We used the same formula to calculate the velocity of a pellet, and the mass here is the combined mass of the pendulum, the string, and the previous 3 BBs. Our total velocity for pellet number 1 came to 913.04 feet per second, and our velocity for pellet 2 came to 932.35 feet per second. And finally, our velocity for pellet 3 came to 959.57 feet per second. This is our equations for the shots of BBs at 2 feet away. Our feet per second on the first shot came to 689.64 feet per second. On our second shot, it came to 734.2 feet per second. And on shot 3, it came to 675.05 feet per second.
Okay, to sum everything up, basically our results were as expected. Once we were able to move the pellet gun back, or the BB gun back far enough that the air velocity didn't affect the pendulum, we got much more accurate results. The fact that we were a little bit under isn't surprising. It is not a new BB gun, so the chances of it still firing at the manufactured estimate of 750 feet per second is not likely.